Hi, everybody. Welcome to another JetBrains webinar. I'm really excited about today's webinar, and I was just talking to our guest in this green room, and he's really excited. But before we get started today, let's get some housekeeping things out of the way. I see there's a lot of people in chat, so that's really exciting. So, speaking of chat, if you're watching this live right now, you can go to YouTube. Typically on the right or bottom right-hand side, you'll see a chat window. There's a lot of conversations happening there right now. And if you have any questions for me or our guest today, please feel free to put them in there. I'll gather them up and then we'll ask our guests those questions at the end of this webinar. Somebody already asked this question. And I'm sure there's going to be more people asking this question. Is this session being recorded? Yes, this session is being recorded. If you're watching this live right now and you have to leave, you can always come back and continue watching. If you're watching if you're watching this video in the future right now, then you know it's recorded. So yes, this video is being recorded. So on that note, I'd like to welcome our guest today. He's UrsEnzler, and he'll be talking about object-oriented versus functional programming with C# and F#. So welcome to the webinar, Urs. Thank you so much for joining us. I'm really excited about this talk.
Hello, everybody. Thanks for having me.
Oh, yeah. We love having you here. You're a .NET Days veteran, so this is more than your first time here on our webinar. So. But on that note, if you're ready to get started,
Okay.
I'll kind of shimmy off and kind of give you the stage.
Thanks a lot, Khalid. So, welcome to my talk about object-oriented versus functional programming with C# and F#. First, a little bit of context, because context always matters. What I'm going to tell you today is based in my experience on building business applications, because my everyday job is building a business application and not some fancy theoretical stuff. So it's a real application in production for 6 years where this main experience comes from. I will use a modern interpretation of what object-oriented and what functional programming means. And if you go and look these terms up in Wikipedia, there is a lot of history there. So maybe it's not a perfect match. And finally, I have to say that I have over 20 years in experience with developing in C#. So I started with C# 1.0. That was a lot of fun back then. And we use F# for 3 years in a production system. So I say that because I often get, yeah, you can do that in C#. Don't you know that? Of course I know that. I know C# much better than I know F# actually. And I will talk about .NET today, so it's all things .NET. So let's start with what is actually object-oriented programming. And in object-oriented programming, the main thing is the object. And an object has an internal state. But you aren't allowed to interact with that state directly. The only thing you can do is you can send a message to an object. And if the object wants to react to your message, it doesn't have to, it can do something. Typically modify its state or send messages to other objects. And that's the core of object-oriented programming. That's it. If we code that, for example, in C#, it looks something like this. We model objects with classes. And we can instantiate the class and get an object from it. And an object here has an internal state, which is called state, to make it simple. And you can interact with this object by calling one of its methods. So these are the messages it allows you to send. The one is multiply by, to multiply its state. And the other one is a method that has a side effect that says, please write the state to the console. So that's more or less the most important thing to know about object-oriented programming. We will see later there is a little bit more to that, but for now, let's keep it that simple. On the other side, if you have functional programming, In functional programming, you don't think in objects. You think in data, calculations, and actions. So data means these are just facts. So I'm a person, I'm called Urs, and I'm 47 years old. That's just a fact. That's data. And you don't change data. Data are just facts. You don't change them. If you want other data, you just create other data. So that's why data is typically immutable. And you can do calculations with that data. So if I have this function f, I can pass data to the function, the input arguments, and the function can calculate something and it returns some other data. So that's why it's often also called, it's a transformation from the input to the output. And important here is whenever I call a function with the same arguments over and over again, I get always the same result. That's called a pure function. When I want to have side effects, then it's called an action. That means the function here is allowed to do some side effect, like for example, calling another service, writing a file to the file system, get some data from the database, write data back to the database. These are all side effects. But again, if I pass in data, it will return some data. But when I call an action multiple times with the same input data, the result may be a different result because it depends on some side effect. So and now in functional programming, if ever possible, we try to model things with data because it's just the simplest thing. If we can't do it with purely data, then we use calculations, pure calculations. And of course, our business applications have to store data. They have to call other services. They have to send messages to service bus. These are all side effects. Then, of course, we use actions. Again, let's look at a simple example here, some F# code. I have a value, and it's important, this is a value. It's not a variable like in C#, because a variable can be changed. A value just says the value 42 is called value. Sorry for this overuse of the name value here. And I can't change that. I can say value means something different later on, but I can't change the actual value 42 here. Then I can define a calculation, give me a value, and I will return the doubled value. That's a pure calculation. For every value I can put in there, I always get the same result. And the last thing is action, because it has a side effect. We write to the console. Again, here I would get always the same result, but the state of the console would change because the result here is no value. So, and you see the main difference when I look at object-oriented programming and functional programming is the concepts which are used to model our solution, or the way we think about how we can design our solution. In OOP, the main thing is that we work with state that we encapsulate in objects and let these objects talk to each other. In functional programming, we build programs by writing calculations that work on immutable data, and if we need side effects, we use actions, as I have shown. So this is the main distinguishment between OOP and FP. The consequence is when we approach a technical problem or a business problem that you want to solve with software, when you think in an OOP way, we try to identify which classes do we use. Maybe we use interfaces because we have different implementations for the same thing. For example, if we have a temperature, it could be Celsius, it could be Fahrenheit. So maybe we model a temperature with an interface with two implementations, one with Celsius, one with Fahrenheit. And then we can use polymorphism. We can say, temperature, please write yourself to the console. And Celsius writes something, yeah, I'm 30 degrees Celsius and the Fahrenheit the same, 70 degrees Fahrenheit. I don't know what the numbers are. So that's polymorphism, as you know it. And because everything is around objects holding states and mutating its state, it makes totally sense that there is mutability by default, because objects want to mutate their state. That's their job. And yeah, to interact with this state, we need to have methods. So OOP makes sense for itself. It's totally reasonable to think in this way, as well as it is in functional way. But we think a little bit different. In FP, because we want to think in data, calculations, and actions, we need something to represent data. And these are the records. So they are immutable facts. Then we also have discriminated unions. So instead of using interfaces for modeling a temperature, I can use a discriminated union, which means a temperature is either Celsius or it is Fahrenheit. There is no third option for now. So this helps the compiler with exhaustive pattern matching. So I want to do something depending on whether it's Fahrenheit or it's Celsius. I can write a pattern matching expression and say, okay, if it's Celsius, do this. If it's Fahrenheit, do something else. And the compiler knows there is no third option. That's really helpful. And because we work with records with this data and just pass them to calculation, it makes sense that data is immutable by default. We just transform them with calculations. And what most functional programming languages know are pipelines, an easy way to chain multiple functions one after the other. We will come back to that with an example a little bit later. So your thinking tools are just a little bit different. And for me, when we work with code, when we work in our business application, the central question for us is, I have a problem now. I want to solve it. Now, is it easier to solve in an OOP style or is it easier to solve in a functional style? And I made a really simple chart for that. The main question is, do you have in-memory state? And by state, I don't mean simple data. Like I'm a person called Urs. State means it's something in memory that I interact with multiple times through its life cycle. Then it's state by my definition. And if I have state, then we prefer going the OOP way, because object-oriented is about interacting with state, with a life cycle of state, interact multiple times, update the state correspondingly to the methods calls you get. That's a perfect match for OOP. If the answer is no, there's a second question. Do you need open type hierarchy? Because if you do, then you probably should go with interfaces. You can always add a third option to the temperature later on. You just implement a new class that implements the interface at temperature and implement all the methods you need. It's easy to extend. So if yes, maybe for example for a plugin system, totally makes sense to use interfaces and go the OOP way. But if you don't have in-memory state and you don't have the need for an open hierarchy, I think going the functional way is much easier. So that's a little bit abstract, and let's make it a little bit clearer. So our system is an attendance time tracking system, and it has a web client, and it calls into a .NET backend. And this is our backend. Because our system grows bigger and bigger over the years, we divided our system into what we call it subsystems. So we have a subsystem for attendance time. So when you come to work, when you leave work, we have a subsystem when you want to go on vacation. We have a subsystem for duty planning, maybe if you have to schedule some duties, and many, many more. There are around 27 such subsystems now, growing. And to call this backend and these subsystems, we just like to put a facade in front of them. So the backend facade, that's the web API that we make calls to from the client. And also every subsystem provides a facade. It's just a facade that hides away all the details in the subsystem. It just provides entry points to call some functionality in this subsystem. So when a request comes in from the client, the backend facade decides, it looks at the routes it to the correct controller, and the controller makes a call to the correct subsystem facade to execute whatever has to happen in this request. Maybe store some data, maybe getting some data. And sometimes we have to call multiple subsystems, so the control is passed back to the controller and it can call a second facade. That's okay. And our experience is that we really like this to have in an OOP style, because these facades have state. It's not very complex state, but it is state. For example, connection strings to our databases. We don't want to get them from the disk or from environment variables on every request. It's just easier to keep it in memory, and it's a little bit faster. That's especially true for things like telemetry clients, which are expensive to create. So we want to keep them in memory. Or things like stuff you need for authentication, connections to service buses, knowing other services, and so on. There's some stuff you really want to keep in memory. And this is the state we keep inside of these facades. And the nice thing with OOP is that the state in the facade is hidden away from the facade of the backend because it's encapsulated. So I don't have to think about it when I'm at the backend level. So in the end, what OOP is great for us is all the stuff we need to compose our system, so that we know how to build up our system so that we can call some functionality. Of course, you can do that in a functional way, because you can build a whole system purely OOP, you can build a whole system purely functional, that's possible. But our experience is this stuff is a little bit easier in an OOP style. Maybe some Haskellers will have a different opinion now, that's okay. But for us, this is easier. Also because the subsystems, you can treat them like a black box if you just call the facade. So that's the whole sense of modularization. You can treat a module as a black box to make working with the code easier. And of course, if you have some extensibility like a plugin system, yes, we want the open type hierarchy. So yes, we want interfaces. We want to go an OOP way. On the other side, for the rest, so for the orchestration happening in the backend and for the business logic in each subsystem, we really prefer a functional way of thinking, because there we have data. We don't have state. Either we get the data from the client passed in the request, or we get the data from a database. But it's just data. We do our operation, we throw the data away. Most of the times. Sometimes there is cache, but the cache is the state in the facade, if you have a performance problem otherwise. So we have mainly data, and then it's easier to work with data calculations and actions. Don't load some data into an object, treat it like state. It just makes things more complex. So a small example, this is a facade written in C#. So it's a class because we want to go an OOP way. It has some fields like the storages, an operation runner, and a notifier. Zeitmeldung is a German word. It translates more or less with a time booking. So for example, when you come to work is a Zeitmeldung. But because it's not a perfect translation, we prefer to use the German word. Because we speak Swiss German, not German, but that's close enough. So we have this state, and we want to keep that in memory. So storages is mainly keeping connection strings in memory. And we have a constructor to pass this state from an outer factory into this facade. And we provide a method, add Zeitmeldung, to interact with the subsystem, and it will add some data into the database. So that's all a facade is about. Of course, it has more methods than just one, but that's the concept of these facades. And you can write the same thing in F#. So this is another subsystem. It's the tags subsystem. So you can tag things with it. And because we like OOP, so this is a class in F#. It's a class because it has a constructor. I pass an operation logger, some senders, some storage, and it also provides two methods. These are the ones called member self-dot. It has an execute operation to execute some command. Yeah, historically we called commands operations. It's just the way it is. And on the other side, you have a query all tags, for example. So again, it's just OOP in F#, no big deal. So, and when we decided we want to have both, we want to have functional concepts in our code, we want to have OO concepts in our code, and of course, when we started our product, we started with C#. So at first, we added a lot of functional stuff to our C# code. The easiest thing probably is using LINQ. It's a functional approach to deal with data. But with the time, we weren't so happy with this functional stuff in C#, and I will show you why now. And I do this with an overview of language features. And there are many language features, so I will skip over many rather quickly because I assume you just know them. And this looks like this. So we start in the middle. And actually, they are not really in the middle. They should be a little bit to the left, but I don't have enough space on the slide. So it's optically in the middle, but actually there are a little bit more object-oriented than there are functional. Because on the left side are the object-oriented things, and on the right side are the functional things. So there are things like dot notation, so that you can write list.length, for example. We have instance member, type-directed name resolution, so that methods are bound to a type. You have implicit constructor, static members, index annotation, named arguments, optional arguments, and interface types. So I assume you all know that. If not, please ask a question in the chat. It's everyday stuff, either as a C# or an F# developer. So then we go a little bit further into the object-oriented side. Oh no, yeah, I switched the order of the slides, so I'm not used to that. We also have a thing like type providers or source generators. I had to change that when C# had source generators, so that's why I stumble over that. A type provider is an easy way to make some data accessible with types. So this example here reads a people CSV, it's a comma-separated values file, and it allows me to access the data in a typed way. So these rows here you can see is person.name, person.id, and they have types. So the type provider is clever enough that it knows name should probably be a string based on the data it parses, and ID is an int. Nowadays, you can do similar stuff in C# with source generators. So you generate some source code that does exactly the same thing. And you can do many other things with source generators. And then in the middle here, there are also object expressions. And this is a really nice feature of F# when working with objects. So for example, here I have an interface iCalculator. So that's the way how we define an interface in F#. You say it's a calculator and it has a method sum, which takes two integers and returns an integer. And then I need a calculator, but I need it only in one single place in my code base. So it would be a little bit overhead to define a class because there is no reuse. It's just in this one place. Then I can say, okay, I want to have an ad hoc calculator. I say the calculator is equal to, and then I use this object expression syntax, which just says, hey, I want a new calculator, and this is the implementation for the interface, just in place. And then I can use it and sum two numbers. And that's really nice, for example, when you have some tests and you have to pass some interfaces to the system under test. And this is an easy way to implement some fakes. So for very simple cases, this is even simpler than using one of the great faking libraries that are around. And we use that, for example, to create our persisters. These are the objects that access a storage. Because they are only defined exactly in one place, we use object expressions so we can skip the overhead of classes. Just a little nice feature, I think. Then we can go further into the object-oriented space now. And there is things like mutable data by default. I have talked about that. Operators on types, outer properties, disposable, and on and on and on. I think these are all things you know if you ever have written something in C#. If you go further into the object-oriented realm, there are large type hierarchies. So if you ever have written code, like me, or suffered under WinForms, you really know large type hierarchies. Because in WinForms, the controls, these were very deep hierarchies of controls. And yeah, on one side it was great, on the other side it was really difficult to handle. And then you have implementation inheritance. So instead of just implementing interfaces, you inherit the implementation of a subclass. And when I studied, and that was over 20 years ago, there was a lot of discussion whether this actually is a good thing or not. And I think this discussion is still going on. Because it's really easy to introduce bugs when you change an implementation in the base class. And then typically there are nulls, and nulls or nowadays nullable reference types in C#. So to deal with the fact that normally you don't want to have nulls. And there is protected members. Now, maybe you ask yourself, okay, protected members, why aren't there internals, privates? You will see that later, why protected members are special. And on the far left side, there are things like self-types, wildcard types, and aspect-oriented programming. So you can do aspect-oriented programming in C# with the help of some additional tools. You can do self-types or wildcard types. If you're interested what they are, please ask Google or nowadays probably ChatGPT. So let's go back more into the side of functional programming. Then you typically have immutability by default. You have seen that. Here, example again in F#. So I have a value which is 3, it's immutable. If I want to have a mutable variable, I have to declare it mutable with the keyword mutable, and then I can assign a different value to the same variable with the left arrow. And of course, I can sum them up. Of course, I can do immutability in C# as well. So the records, there's a way to define records that they are immutable. And of course, I can make a class immutable. I just have to use read-only properties. So that's possible. I can do mutability in F#, I can do immutability in C#. Then there are algebraic data types, a difficult name for actually something quite easy. First, there are AND types. A student, a record, for example. Because it has a name and an age, it's an AND type. It has both, always both. The other side, like the temperature example I used, it's either Celsius or Fahrenheit, so it's an OR type. Because we have AND and OR types, they are called algebraic data types. I don't know if this is historically absolutely correct, but it works for today. And as I have said earlier, this so-called discriminated unions, these OR types, are great for exhaustive pattern matching. That's a real feature of if you go towards functional programming. Yeah, that's an example of a match expression in F#. So a match temperature, I can decompose the values if it's Celsius or Fahrenheit and write them here, convert them to a string. And you see there is no need for this else throw should never happen exception that we have to use when you use switch expressions in C#. For example, when you match on an interface. So it should never happen until it happens because I added Kelvin to temperature. So maybe if you have this scenario, it's maybe better to go the real OO way in C# and use an interface and have a method on the interface that's called, please give me this temperature as text. So then if you add Kelvin, you have to implement it. So it's the safe way. Then there are no nulls. Instead of nulls, we have options. Sometimes also called maybes. So I can say I either have a value or I don't. So this is a discriminated union. Either have a value or I don't have a value. This print even or odd function takes an optional string. Then I can pattern match on these options. If there is a value present, I print it to the console. Otherwise, I print no value. And I can construct such values with some and passing a string or saying none. So you don't have to deal with null. And the nice thing is, if you return a string option, you always have to handle the none case. You can't just ignore it. So you can't just write the bang like with nullable reference types in C#. Yeah, you shouldn't. But yeah, let's be honest, sometimes we do. Sometimes you have to, because it doesn't compile otherwise. Then there is a Hindley-Milner type inference. Another nice name for a very useful feature. If you look at this code, you see I didn't annotate any types. So the compiler somehow just knows what the types are. And the sum when even function, because I write there x modulo 2, x has to be an integer. You can only modulo 2 something when it's an integer. So x has to be an integer. And because I write sum x as one of the cases in the if, it knows the return value has to be an option of int. So it also knows that the none also should return an option of int. And the print even or add function, because I call sum when even if x has to be an int. So I have to pass an int to this print even or odd function. And because I just print to the console and don't really return a value, it knows the return value of this function is unit. So unit stands for I don't have a value. It's something like void, but it really is a value. Then there are list comprehensions. It's an easy way to define lists. You actually can do that in C# when you declare the list array, the list of ints, for example. You can write it like more or less like this. It's a curly braces, not a bracket, but only there. In F# you can use this syntax everywhere. And you can also use for loops, for example, to build up the values in a list. So the result of the second code is the list shown below. Then we have pipelines. Pipelines is an easy way to compose bigger functions out of smaller functions. So at the top, I have 3 functions, add 1, multiply by 3, and square. And I can build a new function called pipeline, where I say, okay, take x, the input argument, then first add 1, then multiply it by 3, and then take the result and square it. So it's like on the command line when you use a pipe. And the really nice thing about this is, in our business logic, and I get in most business logics of a business applications, you had a lot of things. Do this, then do that, then do the other thing, and then something more. You have these steps. And these are just steps in this pipeline. So load the customer, then get the name of the customer. Look, if it's longer than 10 characters, do something. This is how our business logic typically looks like. And the nice thing is you can do that without introducing local variables like you would have to do in C#, or nesting the functional calls one in the other, because then it would reverse the order. So you would have to write square of multiply by 3 of add 1 of x. And that would make the code much harder to read, because it would read from right to left. And at least in the Western world, we are used to read from left to right, from left to right. And for if some F# people are watching, of course, you can also use the function composition operator to shorten that, but let's be real, we don't use that much in our code because it's just harder to read. It's just to scare people away. And not always, sometimes it's really useful. Then there are computation expressions, another fancy word, so I give some examples. When you work with asynchronous code in F#, for example, we can write it like this. So we use this async keyword, and that's the async computation expression. And that gives us some additional syntax. So you can see there's then let bang data. So if you are used to C#, think of it, it's like an await. It says, please call download data and await the result, because that's also an asynchronous call. Await it until the data is there, and then unpack the data from the async result that come back. It's the same like unpacking the value in a task when you write await in C#, for example. So we have the data, and we can do some calculations with it, and then return the result. And this is, again, because it's an async block, it is wrapped around in an async result and passed to its caller, which then again uses let bang. And the nice thing about computation expressions is you can use the same concept for many, many things. So in C# you have async await just for asynchronicity, but computation expressions can be used in a wide variety of scenarios. So it's a little bit harder to understand with async await, but if you understood it, you can use it in many ways. For example, like this. This is the LINQ equivalent of F#, where you can use a query language to filter and group data. So when you write a query computation expression, you get the keywords for, group by, where, select. And you can write it in this pseudo SQL style if you really want to. Never seen code that uses that though. Or very simple computation expressions like the option computation expression, which just says, okay, you give me some optional value. I try and just continue if it has some value. So I try to get the value out of the optional, and the computation expression only continues when there is a value. So I can add 17 and I return an option of the result. If optional has the value of optional is none, it stops executing and just returns none as the overall result. And the nice thing about that is when you write business logic, and you have, okay, first you have to do that, but there may be an error. So I want to get data from the database, but maybe it's not there. Then I want to do some calculation that could fail because the data is invalid. I can just write the happy path and say, whenever there is a problem, just drop out of it. So then I would use, for example, a result computation expression, where I have either it worked or there was an error. And for the F# folks, of course, we could write that a little bit shorter and use option math. But it's just because it's such a simple example here. Another language feature is quotations. And you know that even if you don't know the name, because it's things like, we have a calculation 1 + 2 + 3. That's a quotation. If you know C#, you know expressions. That's the same thing. It's not called expressions in F# because in F# everything is an expression, and that would be completely confusing. then there is a language feature, function currying. Also a short example here. We have a function f that takes 2 arguments and sums them. You see, I like to sum things. And if I use this function and only pass the first argument, as the a, I get another function, which still needs an argument. It still needs the b. But that's a legal thing to do in F#. So I just apply the first argument, and the second argument is still open. And then I can use this function and apply the second argument. So x is actually 1 plus 2. Because add 1 is the same as writing f1 there. So I can just partially apply arguments. I don't apply all the arguments, just a couple of them, starting from the beginning. And that's a nice thing to allow pipelining, because if I have a function that takes 2 arguments, the pipeline can typically only pass the last argument. So I have to apply. I could use add 1 in the pipeline. I couldn't use f. So I would have to write f1 in the pipeline. So that's a nice thing. And it's also a nice thing when you want to do simple dependency injection in F#. You have a function that takes the dependencies as the first arguments, and you apply them in some factory or somewhere, and you pass it to the code that just has to pass in the runtime data. It's an easy way to do dependency injection in a functional way. So, and then are the really hardcore functional concepts, like pure functions, so that the compiler guarantees that all functions are pure, and there are type classes. But again, I won't go into that because you don't have that on the .NET ecosystem. So we are back with the overview. And the fun thing now is to write some to draw some boxes. So if I would draw a box, what is supported by C#, something looks like this. And the reason why it's like this on the right side is that with every version of C#, these tend to go a little bit more to the right. Of course, not surprisingly, C# is very strong regarding the object-oriented features. And again, you also can have AOP with additional tooling in C#. No surprise. And yeah, C# supports some functional stuff. So you can have immutability, you can have no nulls through nullables or through some additional code you write. You can simulate options in C#, of course, but they're less performant. You can simulate pipelines with extension methods. You have quotations, but not exactly the same way as in F#, for example. You have exhaustive pattern matching in the sense, at least the compiler says you should have the else case. So I can also draw the box for F#, and that looks, in my opinion, like this. No surprise, F# is quite strong on the functional side, not on the very hardcore functional side. That's not there. I think it's by design. Donsheim doesn't want to have type classes in F#, but I don't know if .NET would be capable of doing it. I simply don't know. And as you can see, F# is also quite strong on the object-oriented side. And the reason for that is quite simple, because when F# was invented, and there was a lot of base CLR code already there, so we needed interoperability to this code. And there were classes and events and all the things mentioned here. So F# had to understand all these things. So that's the reason why you can use classes, static members, you have typecasting, you have method overloading in F# to a certain degree. So yeah, that's the reason why. So all this is based on a presentation by Donsheim, the inventor of F#. So, but using F# or C# is not just about language features. The question is, are there other advantages of using C# or F#? And for C#, I would say it's just the standard on .NET. So most things built on .NET are built with C# in mind. Also the things that come out of Microsoft. So C# is just the safe bet if you want to use all the libraries, the latest stuff. And there is also more documentation. But with more documentation, there is also more bad documentation. So from learning F#, I found a lot of good F# documentation, so all the things I needed. And also, if I didn't find documentation, the F# community is really helpful. So yeah, more is not always better. But in general, yeah, there is more documentation on C#. And yeah, there are frameworks that are just built with C# in mind, and they are sometimes hard to use from F#. Hopefully, there is an alternative that is more friendly to be used from F#. But our learnings from 3 years of using F# is that when we compare our C# code, and we still have more C# code than you have F# code nowadays, our F# code is just easier to refactor. It's easier to compose things, bigger things out of smaller things, because functions are just simpler to combine than methods inside of classes. And overall, we think it's easier to maintain our F# code than our C# code. And it's not because our C# code is bad. I think our C# code is really, really great C# code. Of course, he learned something in this 8 years, but I think compared to other teams, our code is really of high quality in C# and F#. So it comes down to the language, not design choices. But the most important thing here is interop between F# and C# is really great. So you can call C# from F#, you can call F# from C#. It's a little bit the rougher way, but it works. And we use it a lot in our system because we have both languages. So just use the language that better fits your problem. You can use both in one solution. So to sum up, when do I think we should go the OOO way? When should we go the functional programming way? It's just, I'm repeating myself now. For composition routes where you really have state, yes, we go the OOP way, but only for a complex application. If you just write a small console application, yeah, you can go the full functional way. It works. For the subsystem facade, as I have shown, because I want to hide things behind this facade, I want to use encapsulation there. I want to use this internal state that I don't have to deal with from the outside. So nice OOP thing. And again, if you have something of a plugin system. And we prefer functional programming nowadays for writing business logic. And mainly for modeling our domain. Because the type system, because it knows discriminated unions, gives you just more tools to model closer to reality. And modeling closer to reality means it's just simpler to work with your code. And there are less bugs to some, yeah, we can model that in software. It could never happen in reality, but our software is possible because we just can't model it in a better way. And discriminated unions help with this a lot. I know the C# team is working on adding discriminated unions to C#, but I think they're really at the beginning. So I wouldn't bet on it to come to C# very soon. But it probably will come at some time. And it will be a great addition to C#. And for algorithmic stuff, now, here I don't mean complex, big algorithms. It can be 3 lines of code, but pipelines and working with combined functions is just very easy. And compiler also helps you a lot. At first, the compiler, you think it stands a little bit in your way, but it actually just tries to help you to write correct code. And that's really the case. So that's why we prefer writing the internal stuff below these facades nowadays in F#. But the main message I have for you today is, please, if it suits you, mix both paradigms. Both paradigms have their strengths and their weaknesses. So there is not one better than the other, but I think for writing business logic, FP is better. For writing big applications, how to compose them, I prefer OOP. So please mix both paradigms. And of course, you have seen the graph. If you want to mix both concepts, it's an easy choice of language. So that's from me for today.
All right, very cool talk. I learned a lot watching it. Chat was having a lot of questions for you, so I'll let you take a second, take a deep breath, and then we'll get a lot.
Okay,
we'll get
let's get to it.
But I'll ask my first question because I want to be selfish right now. When your team decided to move from C# to F#, what was that transition like? Did you decide to like rewrite everything with F# immediately? Like, what was the conversation in the room with you and your team when those decisions were happening?
The first thing was that I rewrote a small part of our system, a small slice, a part of a subsystem. I rewrote that from C# to F# to really see what would our code look like in F#. I showed the code to my colleagues, and there was no discussion. It was obvious that for our use case, F# is the better way, mainly because the domain logic was much simpler to read, because we have to deal with a lot of error cases, and we can just hide them away with computation expressions. And the models were much easier to understand due to the discriminated unions. So there was no real discussion then anymore. Of course, the team had to learn the F# syntax. But let's be honest, the hard part when you go to .NET is learning the .NET ecosystem. Like there are package managers and all the library stuff from the CLR, F# syntax. You have to learn 3 or 4 new concepts, all the things I mentioned today. And if you know that, you're ready to go to write production-ready code in F#. It takes a little bit, but it's weeks to really get good F#. Not the best, obviously. You have to learn a little bit more, but it's code that works, that runs. With some mentoring, we were very quickly in adopting F#.
Yeah, I mean, you mentioned the beginning, like 20 years of C# experience and 3 years of F# experience. So, like, folks should probably know watching this. It's like you're not going to pick up any language tomorrow and become an expert. It's a journey about learning and understanding where it works and why it works.
Yeah, it was the same for C#, but the things was just so used to C# and how we solve problems with C#. You have to learn to think a little bit in this functional way. It takes some time, but the nice thing, if you don't know another way, just write it in OO in F#. It's always possible.
Well, I mean, the next question actually asks specifically about that. Like, when you're structuring your code base, how do you structure a large code base? You showed kind of the layers between functional and OOP, but in your particular code base, have you found things that work really well for you?
The first thing, each subsystem is an own assembly in our code. So that's the topmost structuring. And then because F# requires that a strict ordering of files. So you can only reference what is above, inside the file and overall files. So that means we have at the bottom, it's the API or the facade. And then come all the commands, above them, all the commands and all the queries. And then above that, all the domain, the real core domain stuff. And you see the layers directly in the solution explorer. It's not like C# where it's just alphabetically. So you have to define the order. But the nice thing is the order also shows you see the structure of the code in the solution file. And typically we start, let's put everything in one bucket. And if the bucket grows bigger and bigger, at some point, it's hard to find stuff in that bucket. Let's think about how we can introduce more modules, as in sense of splitting up this bucket in several buckets. And then we think about that. So, for example, in the attendance time submodule, at some point, we introduced this Zeitmeldung, these time bookings, as a dedicated module or bucket. And we added other buckets for additional stuff.
Yeah.
So it's just like a fractal. If it gets bigger, split it up again.
I mean, that's also a good point, right? Like you said, maybe when you folks first started, drop everything in the project. But I find too, sometimes it's good to get a working application first and then kind of derive your layers and kind of optimize then.
Yes,
I think
absolutely.
I think a lot of times people try to optimize the structure of their projects and then they get lost in that rather than trying to solve the problem that's in front of them. So
Yeah.
if you're probably getting into F sharp or even C sharp or any programming ecosystem, just solve the problem in front of you. That would
So
be
I have a blog post about the topic. So maybe you can add the link to the description or.
Okay. Yeah. Yeah. I've been telling people to go to your blog because again,
Okay.
I've been finding it very fascinating.
Thanks.
But I guess the next question, you kind of showed this, but how do you actually approach dependency injection in your projects? Are you using that function currying style that you showed us, or are you using something else?
Yeah, the reason I show a lot of our code on social media, but I don't show how we compose things. And the reason for that is that we have a mix of C sharp and F sharp, and that makes things a little bit more complex than they should be if I just go with purely C sharp or purely F sharp. So there are too many layers involved. So that's why I typically don't show that. But as I said in the presentation, for these factories which create all this stuff, we like to go the OO way. We have an object, a class with methods on it. Say, please create this subsystem for me. So this is inside the class, and because we run in Web API, so the outermost thing is the Web API IOC container, because you have to register stuff there so that controllers can be created. And we use plain ASP.NET Core because we have a mixed C sharp, F sharp, so no F sharp specific library here. We just write the controllers in F sharp code for the F sharp subsystems, but it's the same as you write it in C sharp. Not syntactically, but semantically.
Okay.
So we use dependency injection of ASP.NET there. We inject the factory, and all things down we get from this object, from this factory object. But that's just the OO way. There are great blog posts out there about dependency injection in a more functional way. But with our legacy, this is just overall the simpler way to do it. But if you are plain F sharp, there are other options you could look into that more go into this partial application, or even use some reader monad stuff for things. But yeah, that's for me still also advanced.
Yeah. No, it sounds, at least, for me, it sounds like your team's really taking a pragmatic approach. Like it's not about purism or like an ideology. It's about solving the business problems that you have in front of you. And I think that's refreshing to hear, like in a real world scenario, right? So
regarding your question, when we started F sharp, I rewrote the part, but I throw it away because there was no economic sense to really rewrite the whole subsystem into F sharp to just have the same functionality. So the decision then was to write new subsystems in F sharp, make additions to existing subsystems if they're small, still in C sharp. So that's why I still write C sharp and F sharp, more or less on a daily basis. But if you make a major change to a subsystem that is written in C sharp, we have rewritten some subsystems into F sharp because the change was so big that rewriting was not the main work to be done there.
Yeah, that makes a lot of sense. I guess a real like a recurring theme throughout the questions was like, what kind of libraries have you had to kind of use in your C sharp, F sharp uh, application? Is there a lot of things in the ecosystem that you take advantage of, or are you starting to find that you're writing a lot of your F sharp code as is with what's in .NET?
We use a couple of libraries, of open source library that there exist. One of the big ones is, I hope I spell it correctly, is FS Toolkit Error Handling,
Hmm.
which provides a lot of very useful computation expressions to us. Yeah, I wrote a blog post at that. I can't remember. That's the reason why I write blog posts, because I can never remember. So sometimes I wrote about that, so I can help my memory to regain that. Yeah, there are a couple, but not that many. And there is one for helping with interop, task interop,
Hmm.
fusion tasks, I think it's named. There are a couple, but not that many. So basically the F-sharp base library provides the common stuff. It provides the F-sharp types for lists and maps and so on. All the code is there. And yeah, when you use something that is more in a C-sharp style, yeah, sometimes you write a small wrapper function around it. For example, that it's easier to use it in a pipeline, so a one-line wrapper function. But most of the time, we just call as it is.
Hmm.
And yeah. So for example, we use Dapper,
Hmm.
just a normal Dapper, like in C sharp, and it's quite easy to use also from F sharp. So no big trouble there.
That's cool.
There's also an F sharp Dapper adapter, but we don't use that because we use Dapper in C sharp, so we just use Dapper in F sharp.
Okay. Well, I guess it's another question that people are asking, as you went through your journey of like C sharp, F sharp, and kind of melding those two systems together. Were there any books or F sharp reading material that really helped fill in the information gaps as you were kind of learning?
Regarding interoperability, or
Well, just in
I mean,
general, like everybody starts at I guess at a point of
oh,
ignorance, right? You just don't know what exists in the ecosystem. So, are there any
um,
like places you'd recommend who are people who are interested in F sharp go there first and kind of learn?
yeah, absolutely. I started with F sharp for fun and profit,
Hmm.
a really great website with an amazing amount of content on how to write good F sharp code by Scott Wolashin. That's really great. If you have the money and the time to buy and read a book, I would recommend Isaac Abraham's new book about F sharp. It's F sharp in action, I think.
Yeah, I
It's
think
just
so.
it's just up to date. So F sharp fun and profit is 3 years or older. So sometimes the data is not perfectly up to date. But it's
Mhm.
not wrong, but sometimes, yeah, languages have new features and you could do something a little bit easier. But still, it's a great website.
Yeah.
And if you want to just play around, I would go to Exorcism and use the F sharp track of Exorcism. So you can code an example. You have tests already there. It said, yeah, your solution is correct. It has some help. You can look up other people's solutions. So just to play around with F sharp, that's a great location.
Yeah. I've also tried like codewars.com. Like sometimes they have like little examples where you can solve things, and I find like functional languages can typically solve a lot of those questions in like one liners. They're not very difficult.
Yeah, that's
And
sort of typical perfect use case for functional programs, programming languages. But the downside is that people think, yeah, they are only good at that stuff, and that's
Mm,
not true.
that's true.
So F sharp is really a general purpose language. You can build whole systems, whole business applications easily with it.
Hmm. Well, it kind of brings up a good follow-up question. Someone asks how much F sharp is there out in the .NET ecosystem, and is there a demand for F# developers, in terms of jobs? Because that's what everyone always thinks about.
I don't really know. So I don't know how much F# code there is. I know I from time to time I meet people. So, you write F#. I never knew that your company uses F#. So it's a lot of things are taking place hidden. So people don't talk about it.
Mm-hmm.
So, and yeah, I would say it's easier to find a job with C#.
Mm-hmm.
Because a lot of companies they don't actually know what F# is. It's not that easy to switch because you have to have someone who pushes F# in your company. So I don't know. I ask you people if you have numbers about how many F# people are there, and you don't have numbers. As well. So I simply don't know. But of course, there are much more C# developers than F# developers.
Yeah, we definitely have like a JetBrains survey, developer ecosystem survey, so folks can go there and look at kind of the lay of the land in terms of what's happening in the .NET ecosystem. Though personally, I've seen companies that, like you said, are very surprising that they do use F#. One was Grammarly, I think, uses F#. To do like the recommendations when you're typing text and stuff. So that's been kind of cool to see F# find its way into different things. Jet was a big company that used F#, maybe like 5 or 6 years ago. So
yeah, there is where is it? It's fsharp.org. There's a website with companies where companies are listed that use F#.
Mm-hmm.
So the list is quite long.
Yeah.
So it's.
And I'll say this too for people just in general thinking about these things. Companies are becoming more and more polyglot anyways. So finding a pure company that's only a .NET shop or only a Python shop or only JavaScript, I think is going to become more and more rare as a lot of these ecosystems have interoperability between them. So like find the languages you're proficient at and good at and just kind of you'll find those jobs out there. I mean, unless it's like a really weird, obscure programming language with 2 people. So, yeah. On that note, I don't think there's really any more questions. Do you want to say any last thing before I kind of do the wrap up here, or
just
appeals?
Give F# a try. It's a great language for some boring old business application. It just delivers great code.
Okay, very cool. All right, on that note, I'll start wrapping up here with the wind down. So thank you everybody for joining us today. This is a really fun webinar. Thank you, Urs, for coming and giving this talk. I think is very insightful. I definitely learned a lot of things. So for me, selfishly, I love this talk. So
thank you very much.
I was glad to spend the hour here talking to you and listening to your expertise. So if you folks are interested in some of the JetBrains stuff that we're doing, we recently just released Rider, ReSharper, and a plethora of our other tools. Go to jetbrains.com/Rider. Follow us on Twitter. You can read some of our .NET blog posts on blog.jetbrains.com/.net. And be sure you can see more of our content on youtube.com. If you want to hear more from Urs, because I think he does exceptional F# work, I liked reading his stuff. Be sure to go to his blog at planetgeek.ch, and you can follow him on Twitter at UrsEnzler. And as he said, I don't think there's many other UrsEnzlers, so you're not gonna mistake him for someone else. On that note, this is the time where I beg you to like and subscribe us on YouTube. So if you enjoyed this content, you want to see more content, and you want other people to see that content, please subscribe, like, leave a comment. We do read them and we do respond, and we'd appreciate you helping us out there. So on that note, again, thanks, sirs, for joining us. Thanks, everyone, for joining us. We'll see you next time.